Okay, what I'd like to do is talk about a few of the exercises in 4.3 that are here and kind of go over some of them. So the first one I'm going to do, it says suppose two sets A and B are given. Re-express the previous definition of union. So they give you a, oh, that's good, that out of there. They give you this definition of union, right? So here what they're doing is they're showing a union of truth sets, of a truth set between two sentences P and Q. So it's the set of all X and U, so the set of all elements in the universe, such that P of X is true or Q of X is true. And the idea here is that we want to start seeing some of the connections between the logical stuff we did in the earlier chapters and some sets. And you'll see how important sets are, hopefully, by the end of this chapter. So let's see. What I want to do is I want to find a definition for the union of A and B, and what we're going to use instead of the sort of the logical stuff is that I want to use the membership criteria that they've set up. So if A, right, if X is a member of A, X is a member of B, right? So X is in A, X is in B. Those are the membership criteria they're talking about. So if you notice, it's really not going to be that difficult. So if I have a set A union with a set B, that's going to be the set of all elements in our universe, such that the element is in A, or, right, the element is in B. That's it. Right. That's all we have to do. Now notice, when we were talking about subsets in 4.2, and in the book they talk about it, there's at the very end of 4.2, I went over the element method of proof, and notice how useful this definition of the union of two sets would be if you're doing an element method of proof. So let's go to the next one. Develop a useful definition for set equality. This is very important because if we want to say two sets are equal, right, with some quantified logical statement, that means the same as A equal B for two arbitrary sets, right? Now you remember two sets could be equal if they have the same things in them, right? So if they contain all the same things, we would say that those two sets are equal. But, maybe what we want is something a little bit, I guess maybe something a little bit broader than that. So one thing I could do is to say for A to be equal to B. If two sets are equal, then a common way we might express this would be that A is a subset of B, right? And that B is a subset of A. if we want to say something is a subset, right, we could say that all members of A are members of B, and that all members of B are also members of A. That's usually what we mean when we are talking about subsets and set equality. Now, another way we could kind of think about this is to say that if I have a set equal to another set, and maybe I want to use some logic, right, to sort of say what this is, well, one thing we could think about is that the set here is going to be the complement of A or B. And B complement or A. Something along those lines. It's pretty close to what's happening there. Now, hopefully you can start to see this. One thing we said, the last exercise I want to go over, it says what symbol in logic should go between the membership criteria, member of A, member of B, if A and B are equal sets. Well, let's draw our attention to this here. And in the last chapter, we have this kind of odd thing where for A to be a subset of B, right, that means for all x, we'll say for all x in U, if M AX, I'm going to have to erase this thing a little bit. If this, then, right, M B X. So that would mean that for B to be a subset of A, we would have something very similar for all x in U. And if you remember from logic, we had this idea of if P then Q, and if Q then P, right? Well, what would we put between P and Q? Would be P if and only if Q. Right? So this is from like chapter, I think this is from chapter 2. Whoa. So this is from chapter 2. And notice putting that all together, that would tell me that if for A to be equal to B, a way we could write this in sort of like with the sort of logical form. So this is equivalent. I'll just write a weird little equivalent symbol. Saying A is equal to B is equivalent to saying for all elements in the universe, we would say like im A, so X is a member of A, if and only if X is a member of B. Right? And that kind of makes sense if you think about it, what they're saying, that if the sets are equal, an element that exists out in this universal set is only a member of one if it's also a member of the other, right? So it has to be member of both, right, in order to be a member of either of them, right, since the sets are equal. So if I said, that two sets are equal, and I gave you a member of set A, right, you could tell me that that's also a member of set B. Right. And this also kind of goes to the early on definitions we think of two sets being equal if they contain the same elements, right? Okay.